Okay, the next thing we're going to be considering here is the function e to the x, and take a little bit closer look at that function, what its properties, what it looks like, the graph, and several things about this function. This is one of the more important functions you'll be dealing with, in particular when you go into calculus. This function has special properties that no other function has. It's a very important tool to be able to use in the calculus sequence and in differential equations. And so some familiarity with it is going to be a really important thing for you. First off, let's talk about the graph. I mean, you can graph this with any calculator or a graphing utility, but approximately the graph looks like this. This is a rough sketch of the graph. Any exponential function with the base b greater than 1 has this basic shape. Recall that for any exponential function, the base has two restrictions. The base must be greater than 0 and not equal to 1. Now that falls into two categories. The base could be a number between 0 and 1, 1/2, or a decimal, 0.4 value like this, or the base could be a number bigger than 1. So long as it's greater than 0 and not equal to 1 is permitted. Now, what would this look like? This would look like, in this particular case, if the base is a value between 0 and 1, then the graph roughly looks like this. If the graph base b is bigger than 1, greater than 1, the graph roughly looks like this. Now, the specific details depend upon the specific values for b. In this particular case, recall that e is approximately 2.718, yada, yada, yada. It is greater than 1, and so it meets this requirement, and so we may use e to the x. We treat e as if, rather like we would treat pi. It's a letter that represents a specific constant, and so we have e to the x. Now, some specifics about this particular graph. Domain. The domain consists of all the x values which you are allowed to use for input for this function, and the domain of the function f of x equals e to the x is all the real numbers. So you may write the negative infinity to infinity version, or you may write the double stroke r version, which is what I tend to use, but those are the same thing. So either the negative infinity to infinity or the all real numbers symbol, they're equivalent. That's the domain of the function. The range consists of all the y values that gets used, all the values which are used as output for this function. Notice that this is asymptotic. The graph is asymptotic to the x-axis. It never actually touches the axis, and so 0 is never actually achieved. And so the range consists of all the positive values. Every value from 0 to infinity is the positive value, so that's the range of that function. Again, 0 is never achieved. Now that's a key notion here, the fact that the graph of e to the x never touches the x-axis. Now, if you shift this, if we take this graph and shift it downward, we know that when you add or subtract a quantity outside this primary function, that corresponds to a vertical shift. And so certainly, if you take f of x is equal to e to the x, let's say -2, that would shift this graph down 2 units, and then yes, it would have an x-intercept. But when I say this graph has no x-intercepts, what I mean is the basic shape exponential function. This is true of all exponential functions, not just e to the x, but irrespective of the base, the x-axis is an asymptote. And so for any exponential function, basic shape exponential function, the graph of the function never touches the x-axis, 0 is never achieved. And so for any of these scenarios, the range is from negative infinity to 0. 0 is never achieved. And here's what that means. Recall, let me get rid of this. Recall that when we graph a function and we want to find the x-intercepts, if this is y equals f of x, if this is some function from back in our basic algebra days, and we want to find the x-intercepts, the way that is done is you set the function equal to 0, and then you back solve to find the values of x that make that true. And so setting the function equal to 0 is the same procedure, or that's the procedure for finding the x-intercepts. Now, consider this function. This is the basic shape parabola, shifted up 1 unit, so we're all familiar with that. This does not have any x-intercepts. Clearly, we know that from the graph. And so if you set about trying to find them, if you set x squared plus 1 equal to 0, if you try to find the x-intercepts, in this particular case, you stinking better not find any. And sure enough, if you solve this, you get x squared is equal to -1. If you try to take the square root of both sides of that equation, you get the square root of -1. So I get x is equal to positive or negative square root of -1. For in the real number system, this has no solution. Remember that no solution does not mean wasted time. No solution does not mean you haven't done anything. No solution means whatever you're looking for, there aren't any. Here, we are looking for x-intercepts, and the fact that we got no solution means there aren't any. If there are no x-intercepts, that means setting the function to 0 and solving should not give a solution. And that's what's happening here. If we look to try to find the x-intercepts of e to the x, and we set this function to 0, if we set e to the x equal to 0 and try to solve that, from the graph, we can see this has no solution. Because the graph has no x-intercepts, that means this equation may not have solutions. There is no solution here. If you set e to the x equal to 0, that equation has no solution. That needs to go into your brain, and you keep that and have it there when you need it for the calculus sequence. Because this is the kind of thing that you will encounter. You'll see equations that look like this. Now, where they come about, that's something you take care of in the upcoming semesters. But you will inherit, we joined this problem already in progress, you will inherit a problem that looks like this. X e to the x minus 2e to the x equal to 0, solve. Solve that equation. Well, you factor out e to the x. Now, if you factor out e to the x, you leave behind x minus 2. When you factor, you set each of the factors equal to 0. Now, this is straightforward. Here we have x is equal to 2. But what do we get here? Well, that's where you bring this to bear. E to the x equals 0 has no solution. That doesn't mean wasted time. It means this branch of this equation solution procedure did not generate a solution. So the only solution here is 2. So in this particular case, whatever the interpretation of this was, whenever you get to the calculus sequence, the point is, if you solve this equation, the solution is x equals 2, and this piece does not give a solution. So the function e to the x. The domain is all the real numbers. The range is from 0 to infinity. Do not include 0. And an important piece, if you set e to the x equal to 0, you get no solution. So those are sort of the basics of this function e to the x.